All right, folks. Welcome to the 13th annual Brinson Lecture. I'm Mike Ladders. I'm a professor at the University of Chicago in the Astronomy and Astrophysics Department. And it turns out I'm going to be your MC for the evening. And we have a musical interlude. We'll just wait for that. This gives me a chance to read my speech one more time, which I put on my phone, which I realize is too old, and the screen is too small, and my bifocals need adjustment. So if I end up looking down a lot and don't have very good flow, pardon me. So we're here this evening to get an inside look at the deployment, commissioning, and science operations of, quite frankly, the best telescope ever built. And I say that as someone who is actively using it and absolutely loving the data that we're getting from it. And we're going to get this look at it from someone who has been right in the thick of that process. So this is the 13th annual Brinson Lecture. This lecture series began in 2008, and it's possible due to the generous support of the Brinson Foundation, for which we are very grateful. The foundation also supports early career scientists at the University of Chicago and the Astronomy and Astrophysics Department, and they're really an ongoing partner in our quest to unravel the great mysteries of the universe. The foundation is a privately funded philanthropic organization that provides an opportunity to focus the Brinson family's common interests in encouraging personal initiative, advancing individual freedoms and liberties, and of particular great interest to us tonight in positively contributing to society in the areas of education and scientific research. They're particularly interested in support for fundamental science and advances in technology in the fields of astronomy, astrophysics, and cosmology. Now, the arithmetically inclined amongst you, and I assume there are some in a crowd like this, probably just put two of the numbers I just said together and went, wait, hold on. The 13th annual lecture started in 2008. And it certainly is 2023, isn't it? Well, I want to remind you of two things. So first of all, many of us in the department are cosmologists of one form or another, and we work in non-Cartesian space-time, so things don't always line up the way that you might expect. And the other, my working mantra for the last few years is pandemic years don't count in a lot of ways. And given that today was actually the official end of the COVID emergency declarations in the US, I am particularly delighted to gather with you all in this way and return with a full heart and voice to what's really a highlight of the year for us. Now, this series, this is our 13th time. Speakers in this lecture series have included Nobel laureates Kip Thorne, John Mather, and Andrea Ghez, pioneering exoplanet scientist Sarah Seeger, and the astronomer royal Martin Rees. Now, our 13th Brinson lecturer tonight, Dr. Jane Rigby from the Goddard Space Flight Center, is a wonderful addition to that pantheon of accomplished speakers. Dr. Rigby is the project scientist for operations for the James Webb Space Telescope. As we'll hear tonight, she has been deeply involved in the commissioning of the telescope and the transition to full-time science and operations. And she is the lead author, along with a mere 625 co-authors, of a recent major academic paper that details the performance of the telescope and the instruments. Spoiler, it's fantastic, okay? She's a deeply engaged citizen of science who has been recognized by many organizations for her leadership and scholarship. She is a trustee of the American Astronomical Society. She was recently named by Nature magazine as one of the top 10 people who shaped science in 2022, and also in 2022 was named the LGBTQ Scientist of the Year by the professional organization Out to Innovate. On a personal note, I'll also say she's been a dear friend and science collaborator for about a decade and a half. It is thus with a great delight that I give you Dr. Jane Rigby, who will describe for us the era of the Webb telescope. And before you clap, just one note, hold your questions until the end, and we'll have a question and answer, pass a microphone around at the end of Jane's talk. Jane Rigby.
Thank you, Mike. Thank you, Mike. Thank you so much for having me here, the Brinson Foundation, the University of Chicago. It's really nice to be traveling again and to get to tell you what we've been busy doing and to share with you the story. I have two stories to tell you about. One is about the telescope, what it is, what it does, and I'm going to not talk about the 20 years it took to build it, test it, and get it ready. I'm just going to pick up the story with getting it into space and then getting it to work. And then I'm going to tell you a story about, really it's a story about us. It's a story about like how we got here, how the Earth got here, how the galaxy that we live in got here, which is really the science that we're doing, is how's it all work? Where did we come from? So the first part of this is the story of the telescope, this lovely, complicated beast. And we built this thing. It doesn't look like any other telescope on or off the Earth. It's huge. It's 2 stories tall. It's got this sunshield that's the size of a tennis court. You can see the little people in the picture for scale. They're regular-sized people. It's just a big telescope. Up on the cherry picker, right, to get a sense of scale. In this picture, the secondary mirror is folded up because it has to fit in the rocket. This is a telescope that is bigger than its rocket. And so to get it into space, we had to fold it up. Fold up the big golden primary mirror, fold up the secondary mirror, and then fold up that 5-layer sunshield to get it all furled up, get it into the rocket, launch it into space, and then in the dark, a million miles away from home, with nobody to help it out if it got stuck, unfold it. And that's what we did, and it worked. So this is just a sense of what this thing looks like. Here it is in Northrop Grumman at the clean room in Los Angeles. Here it is a side view to get a sense of just what it looks like. You can see those 3 mirrors that are pointed toward you. Those are the 3 of the 6 mirrors that were folded up for launch. So those mirrors 3 on one wing, 3 on the other wing, were folded up behind the telescope for launch, and then unfolded and locked into space, locked into place once we got into space. So that's the thing, and you can see the sunshield fully deployed. All of this had to be tested on Earth in a gravity, right? We can't do it in a, we're stuck being on Earth in gravity. And it has to operate cold at 40 degrees above absolute zero, so we have to be able to test it in basically the world's largest thermos bottle, okay? But I'm not talking about the 20 years of construction and building. I'm not gonna talk about that. We're gonna jump ahead. So this is what this thing is. This is just, again, to get a sense of scale. This is just the telescope before we had attached the rest of it, before we had attached it to the spacecraft that has, the little thrusters and the computer and the rest of the thing the spacecraft needs. This is just the telescope. You can see the blurry part. You're not allowed to see that part. It's blurred out. Goes by fast. So this is just what this thing looks like, right? It is a 2-story tall, 6.6 meter across telescope that is now in deep space. And we built it, it was assembled with pieces all over the United States, and then it was assembled at the NASA Goddard Space Flight Center, which is just outside Washington, D.C. And one of the cool things about it is it was assembled in this big clean room that has a viewing window. This thing is huge. This is a very clean room. It's about 10,000 times cleaner than the air you're breathing right now. Everybody's in bunny suits. And in this room where people were working nonstop for the better part of a decade getting this thing built and then shipped. And there's a viewing window. So on a lunch break or after work, you could stop by and go see how the telescope was doing. And it really is kind of we all got an email one day saying, hey, we're gonna move the telescope, come take a look. And I'm in there, my boss, John Mather's in there, a bunch of us are there like, oh, Leah, take pictures, right? Because it's amazing, you can see yourself reflected in this mirror that we knew was going to be a really big deal. It was like, if this works, this is gonna be huge. This is either gonna be a really big deal or a huge embarrassment, one of the two. But nobody knew it yet. And so we would stop by after work and say hi to the telescope. And over the whole process of building it and constructing it, you got to see it all build up. I would take my kid after work, so that's him a lot smaller than he is right now. And the techs would all say hi to him, like, no, don't just do your job, pay attention. But we would come in at 6, 7, 8 o'clock at night, and they're working, building the telescope up. So it's been neat that I can look back through my photos and it's like a family album of seeing the telescope be constructed as well as my kid getting a lot taller. I asked him for permission to have this in the talk, and he said, only if you show a picture of me now to show that I'm not a little baby anymore. So I have kept my promise. Okay, he's 10, he's on a giant pile of compost. There, okay, he's big now. Okay, so this thing then had to fold up to fit into the rocket. It rode on a custom shipping container on the LA freeways at 4 in the morning down to a boat, and then rode through the Panama Canal. They're picky about that, to the launch site in French Guiana. So it was launched on an Ariane 5. That's a European rocket. This was a multinational, multi-agency mission. So the NASA was the main agency with cooperation from the European Space Agency, ESA, and the Canadian Space Agency, CSA. It was launched on a European rocket. Here it is down in French Guiana, unpacked and ready to go into the rocket. All right, so here's the timeline, skipping 20 years of work. Not there. We go to launch, and then something in the middle, commissioning, which I'm going to talk about. What was all that? 6 months of secrecy while we worked our appendages off to get this thing to work. And then at the end, in July of 2022, the end of commissioning, but the beginning of science, we released our first images showing that, yes, indeed, the telescope works, and in fact, it works better than we could have, and we dared hope for, honestly. We've been in science operations now for about 10 months. We started in July. And so when I wrote this talk, I realized I didn't have a launch video because I didn't see the launch. I was in the operations center getting ready to actually start operating the thing and telling it what to do. But I got to see the video later, and I was like, okay, we got to have a launch video. So I added it into the talk, okay? So, and it has very loud and very impressive music here. So this is the rollout to the pad. And then it launched in French Guiana on Christmas Day. The little retrospective of the 20 years of work that it took to get it there. They count down in French because it's a European rocket.
And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So a lot of my colleagues, of the people working the mission, were down in French Guiana for about 2 to 3 months, taking care of the hardware, testing it, making sure the telescope was safe.
Quite a Christmas present for the world's astronomers.
And then got on the next plane home to do commissioning. So that's our project manager there.
And we have a fully deployed
This is us in Baltimore.
JWST
This is realizing, this is actually the unfolding. It was supposed to be the wave, and they messed it up. So we were all in Baltimore. So that's the NASA PR version of the launch. I want to kind of tell you the more intimate version of the launch, at least as I experienced it. We were in Baltimore, which is where the mission is operated out of at the Space Telescope Science Institute for launch day with our matching polo shirts. And I was on console for launch through to the middle of the day. This is the 1 minute we had to take a selfie of my team. This is Susan and Mike, the folks that were there on duty, and there were other at launch plus 43 minutes. So the only deployment that we actually saw was that deployment of the solar array. All the other deployments we didn't have video for. I grabbed this out of the Project Science log because for me this was one of the most emotional moments of the mission. If we don't have a solar array, we don't have a mission, we're just done. You need solar power, right? The battery only lasts a couple hours. So the solar array came out, and we're all on voice loops. We're all listening to to each other's audio, and the electrical engineer reported that there was current on the array, and that they were getting voltage, right? That yes, indeed, they were getting power. And I don't know that I can convey to you how much emotion was in that very technical, dry phrase, there's current on the array, but that is we have a mission, it's working. Okay, good. Because if that hadn't worked, there were things we could try, but we needed power or we wouldn't have a mission. So there it is, the shiny solar array, yes, it works. We also fired the mid-course correction later that day at 12.5 hours. We fired the rockets that are contained within the telescope itself to send it 1 million miles away to the second Lagrange point. And then we were all off shift. And so, of course, this is December 2021, December 25th, peak Omicron COVID. So we all were masking and of course, and then testing every day, and having a glass of wine or beer to celebrate that evening after we were off shift, just to be very clear, after getting on console at 4 in the morning, and then getting off, most of us at 4 in the afternoon, having a beer to celebrate that this thing had worked, that the launch had worked, and we were headed to where it was supposed to go. In fact, we knew within a day that the launch was perfect. And by perfect, I mean good to a part in 10 to the 4. It was exactly what we commanded it to be. And that has led us to get more years of lifetime out of the telescope. Which is great, right? We have, and that's really exciting, and that's due to the diligence of our engineers, who both, the folks that designed and executed the rocket to get it to give us that perfect launch, the mid-course correction that was done perfectly, again, to like better than 1% to get us to where we needed to be, and then the engineers who over the years had managed to keep the weight down as much as possible such that we could take the extra weight and put it in the gas tank to get a little extra life. And then of course we woke up the next day and kept going. Again, but we got to sleep until 4 in the morning, so that was really exciting. So now, oh, by the way, everything in this that I'm going to show you is real pictures. I'm so tired of artist conceptions, and I have tried to put this is fake, this is not real, everywhere that I have an animation, okay? So the telescope is now about 1 million miles from Earth, 1.5 million kilometers, and it is in an orbit that is following the Earth in a Lagrangian, second Lagrangian orbit. So it just goes along with the Earth. This is a nice stable orbit because it's never an eclipse, and it never sees the same amount of sunlight and the same amount of Earth light all the time. All right, this is also fake. These are the deployments, but this is what the telescope did. And I used to not show this to astronomy departments when I would go give colloquia, because the astronomers would look at it and say, well, that's never going to work. I think, but it has to work, or we don't have any astrophysics for the next decade. But yes, it does work. This is the sunshield coming out after the pallets came out. That's the secondary mirror, and then the primary mirror segments. And believe it or not, it did all of that exactly how it was supposed to. None of that, here it all looks very robotic, and it happens automatically. In fact, all of those deployments were commanded from the ground, and we were watching every little piece of telemetry as it was coming back to tell us that, yes, indeed, that's moving as it should. And that's moving like it did in ground test when we tested it on the ground. And so all of those were done by hand. There are times where we would pause and say, did it do that and test? And then we'd go back and, yep, it did. Okay, fine. And then we'd carry on. But all of these deployments, we had the NASA, I think we were billing it as 30 days on the edge, which means 30 days of being scared that this isn't going to work. And in fact, it all worked incredibly smoothly and faster than we expected. So this is the deployed configuration of the telescope now. That sunshield it's now just static for the rest of its life. Its deployment is done, and those engineers are all off onto other things for a tremendous amount of work to get it to work. The only thing that's wrong with this animation, which is not real, is that you can see the telescope, okay? And of course, the telescope is hiding in its own shadow. It's hiding in the shadow of that sunshield. So anytime you see a picture of the telescope, of the Webb telescope, where you see those beautiful gold-coated mirrors in sunlight, that's wrong, and you can feel superior, okay? The bottom side of the telescope, right, the sunshield is down here below that, or like the solar panels and the spacecraft that are all toasty warm. And then up at the top, the telescope is 40 degrees above absolute zero, right? Really, really cold. And it's that cold to be able to see into the infrared. And I'm going to show you why we have to do that. We have to, basically everything, you, me, we all glow in the infrared. And we glow more the hotter we are. So we need to get the telescope very, very cold in order to be able to see the faint glow of stars and galaxies from deep in the universe. I want to just point out that about 20,000 people built this telescope, and it is just amazing to me the dedication and the effort on this mission. I just finished reading a book about the Wright brothers, and this quote really struck me that, yes, the Wright brothers were smart, but what they did, lots of other people could have done. It was an incredible amount of dedicated, focused work. And I really see that in our engineering team. Our optics folks also have the world's best team photo, right? Because that's them reflected in the mirror that they built. Despite all of the very stirring soundtrack, most of the actual 6 months of commissioning looks like this. A lot of us sitting around a conference table, looking at data, looking at results, scratching our heads, thinking, all right, well, maybe we should try, and just doing the teamwork to get the thing to work. So that's what it looked like. It so happened this is the day we were getting ready to find out if any light was coming through the telescope. Because there are 18 primary mirrors, they don't, when we launched them, we didn't try to get them to be perfectly lined up on the ground because we were just going to shake the heck out of them once in the rocket. So instead, we built actuators on the back that can get them to where we want them once it gets in space. It just so happens that there was Mike with the camera our camera guy was taking pictures that day, so there's a nice, very stirring picture. But this is what it looked like. We were looking at data and trying to figure out what's going on. And okay, we knew we were being photographed, so we kind of did a little clappy clap. But that clappy clap is, yay, we took blurry images. Yay, light went through the telescope. There's no lens cap in the way. This is great. The next task was to get those 18 mirror segments to work together like one telescope instead of 18 separate telescopes. And so we did that this night. First we have to find each of those little 18 segments. So we did that that night. This picture actually does capture some of the stress that we were feeling to see, okay, is any of this going to work? We pointed at a bright star, and then we kind of searched around to try to find those mirror segments. This is the same picture but then flipped around. I took this picture, and then, Marshall took this picture, and then I took the next one of Marshall. We started scanning around the sky to try to find each individual mirrors, the blurry image from each individual mirror, and they started popping up. We spent about 30 minutes where we couldn't find any of them, and then they started popping up, and we got really goofy really fast. You can hear Marshall counting up and trying to get to 18, but losing count. That's what it felt like. We were like, oh my gosh, yes, light is going through each mirror and getting into bouncing off each mirror and getting to the telescope. We should put numbers on them. So within about an hour, there was a beautiful display of all 18 blurry images with numbers on them. And that was supposed to be a several-day search, and in fact, we got it done that evening. It was fantastic. But at that point, we had 18 blurry pictures. There is then, if you see the flow chart to the right of Marshall there, that was the flow chart for the sequence of getting all the way to one beautiful image. And it was a beautiful set of optics and physics to measure where each mirror was and then correct it so that they were all working together as though it was made out of one piece of material rather than 18. And that process took about a month. And then we had our first image that showed that, yes, indeed, the telescope would work. And we took that image on a Sunday and did a press, and then we're sitting on a stage talking about it on a Wednesday. It was all very fast. And this is what we showed. We didn't want to overpromise. Okay, yes, it's working. But in fact, it looked something more like this. There were galaxies everywhere we looked. And this was not even an hour-long image. This was like 2,000 seconds. And so I remember downloading this image on a Sunday morning at about 9 or 10 in the morning in my pajamas, and getting this onto my computer, and I was like, all right, this is going to work. This is ridiculous, right? Because this is yes, this is kind of ugly. This is what the raw data looked like straight off the telescope, okay? Because I want you to, we then cleaned it up to be in 3 colors and to be a little splashier. But, this is full of galaxies. There's thousands of galaxies everywhere you look. And so this for me was that moment in March 13th, 2022. It was like, oh, okay, this is Nobody knows this yet, but this is really going to work well. And then, realizing that the images were sharper than we expected. And so this is the difference between what we were used to on the left from the Spitzer telescope and what we have now with JWST. It's just so much sharper than anything we've had before. It's like, I would say it's like getting your first pair of glasses, but it's not. It's a bigger change than that. Just the whole universe is both really sharp and we can see very, very deeply. So I'm going to breeze over the next several months from going from that first focused image to getting all 4 science instruments and all 17 science instrument modes commissioned, that they were checked out, we had tested them, they were working like they were supposed to, which meant that we were pretty confident that when we started taking data, it would be what we expected. And then in July, we started taking data. So at that point, we had not done any science. In fact, we all took a vow that we wouldn't do science, which is a hard vow, I gotta tell you. I like doing science a lot. I measured the flux of how bright a lot of bright stars were. But then we took our first science images, and again, vowed not to do science with them, but got ready to show them to the world. And so I got a text message saying, can you show up at the White House in a couple days? And the answer is yes, sure, okay. And so we got to present those images to the president and the vice president. And I'm not saying that to be like, haha, I went to the White House. No, like it was really a once in a lifetime experience. But I'm telling you this to say that it was really neat that astronomy got to be front and center for an evening. And we got to talk about the big stuff, the big picture. And it was really fun because, I had been instructed, like, do not waste the president's time. Okay. And when we got there, like, they didn't actually care, they didn't vet what I said, they just wanted to check how long it was, which is okay. But then I got there and they kept asking questions, right? The president, the vice president asked questions because it was really fun. They were like, wait, hold on a minute. How can we see back 13 billion years, right? So it really was a chance to show the enterprise of what we're doing, what modern astronomy can do, and what these space telescopes can do. And so in the second part of my talk, I want to show you what we can do and what we're doing with the telescope. The next day, that was July 11th, the next day, the first images came out and the goal was to make the front pages of every newspaper in the world. Yes, there's still newspapers, and it did. So that was great. We got to do a little media broadcast on this little stage this lovely stage that our media folks put together, and that was actually really kind of fun. And again, they told me how long I could talk, but they didn't say what I had to say. So I got to geek out about what I'm going to tell you now is about how we understand what galaxies are made of and how they work. And nobody stopped me, so that was fun. So it was also a demonstration that the telescope really works and that in a couple hour integrations, just, the kind of science that we can do, between breakfast and lunch would take Hubble weeks or is utterly impossible with Hubble. So I want to show you some of that science now. But first I need to show you a couple things that are fake, but I'm going to tell you that they're fake. Okay, so first, I'll show you something real, then fake. All right, so I want to talk you through the science that we're doing. And really, for me, I think that a way to think about it is just the story of how it all came to be. How did we get here? How did galaxies form? How did stars form within galaxies? How did planets form? And then what are other planets like? How weird is our solar system that we're, quite fond of? The very furthest back that we can see, the furthest that we can understand about that story is really the echo of the Big Bang. The Webb telescope cannot see that, okay? So this is not something that the Webb telescope can see. This is the cosmic microwave background. It's from about 300,000 years after the Big Bang, or 80,000 years after the Big Bang, and it is the afterglow of the Big Bang. And it's amazing that we can see that, right? That is the furthest back we will ever see. At that point in time, the universe is a hot, hot place. It is cooling from after the Big Bang. There are no galaxies. There's no stars. It's all just hydrogen and a couple other small amounts of elements made after the Big Bang, made in the cooling. And there's these little hot spots and cold spots, right? And the hot spots and the cold spots correspond to denser and less dense regions. And those are going to collapse over the next 13.7 billion years and form things like galaxies and galaxy clusters. And so that's the picture of the Big Bang, of how this is the picture we have of how the universe has evolved, right? So JWST, the Webb telescope, picks up this story later after those little dense things, which are mostly dominated by dark matter, not stuff we can see, which is mysterious and we don't understand what dark matter is. After that matter has condensed, and the gas that's coming along for the ride has cooled, and you're able to start forming some stars. And so this is fake. Okay, that one was real, but this one is fake. This is a simulation of what that might look like. And so this is a computer simulation using the conditions as we understand them by studying the microwave background of what the Big Bang gave us, of understanding how the first galaxies might form. Right, so it's looking at these dense condensations that get dense enough you can light up some stars. And this is showing the ultraviolet light that can come out of those stars that can actually blow away their environments. So that's the picture we have, in which it starts out small and it starts out in little galaxies, and then you get at some point the whole universe starts lighting up, and you have galaxies all over. You also have this picture in which these galaxies start really small, and then they merge to form bigger galaxies. And then those merge to form bigger galaxies. And this is this picture of hierarchical structure. That's happening right now. Our Milky Way is eating our neighbors, or making a bigger party with them, depending what metaphor you like. It'll take a while, though. So that's not real. Let's go to something that's real. So this was the first image that we released. This was the image that the president released a year ago in July. And I want to walk you through what this is, because this is real data from JWST, and this really shows how we're able to do what we do, okay? So there's a bunch going on here. This is a complicated field. Okay, there's a bright star. That's from our galaxy. Ignore it. It's just photobombing. And then in kind of ghostly yellowish white are galaxies in a cluster of galaxies, like a big city. And those galaxies we're seeing as they looked about the time the Earth formed, right? About 4 billion years ago. And as we zoom in here, you can see that this whole field is just full of galaxies, right? And those red ones, the one that look warped and distorted, like you're making taffy at home and it all got a little messy, those are galaxies that we see behind the cluster. Okay, and we're seeing them further back in time. So let me back up for just a second and say what I mean by seeing back in time, because it feels like magic, but it's real, okay? And it's key to understanding the rest of this talk. So you are seeing me a very small fraction of a second in the past, right? Because the light has to bounce off of me and get to you, okay? Who cares? I'm the same as a couple of nanoseconds. Nothing's changed. When you get light from the sun, that light, it has been traveling through space for about 8 minutes. Who cares? The sun is the same 8 minutes ago. When you look at Jupiter, you're seeing it as it looked about 40 minutes ago. Okay. But when you start looking out to stars, you can see them as they looked years, tens of years ago. If you care, you can go find a star that is as many light years away as you are old, and then you can, that light that's arriving right now, great. It left when you were born. Nifty. But again, nothing very profound yet. Now start looking at distant galaxies. Look at these galaxies. These galaxies are so far away that the light has been traveling through space for billions of years. So those fuzzy white galaxies that are in the galaxy cluster, that light left about 4 billion years ago, and it's been traveling through space for the intervening 4 billion years. And now we're just detecting it. The reddish galaxies in the background there, we're seeing much further away, 5, 10, 11 billion years into the past. And so we're able to take these snapshots of what galaxies looked like at different times, right? And so, we can see the galaxy at the lower right there. That's a galaxy that we're seeing, let's see, yeah, that's like 4.5 billion years after the Big Bang. Okay, great. That one on the left, though, that light left that galaxy 13 billion years ago. So we're seeing back in time for most of the age of the universe. The universe was only 700 million years old when the light left that galaxy. That's really cool, right? That's seeing back. And so that's what the telescope was built to do, is see back to the first billion years of cosmic time. And in the very first image and data, we showed that that's possible, right? It really is rather, this is the spectrum that we took of that galaxy, and it's a fingerprint. Anywhere in you get that fingerprint, the pattern there of those little spikies sticking up, and they tell you that you've got hydrogen, oxygen, some neon elements, and they can tell you exactly how far away that galaxy is. And so this was what the telescope was built to do, to not only find galaxies very far away, but tell us exactly how far away they are and what they're made of. Just really kind of just, so it was working just like it was supposed to. Okay, so that was one of the 4 science goals. We can also do many spectra at once, because there's this really cool feature in one of the spectrographs that can pick which galaxies we want to look at and pull just them out and then do spectra of those. So that's fantastic. We're able to pick galaxies at different look-back times and from them assemble a history of how it works. We never get to see a galaxy evolve because we don't live long enough, but we get to see what galaxies look like at different ages of the universe and from that piece together that story. The telescope has been fantastic at doing that. This is the record holder currently, which down here on the right, that little red speck, we're seeing as it looked 320 million years after the Big Bang, right? So just a fantastic, the plots are, for an expert, will look at those and say, yep, that's how far away that is. Lovely. This is currently my favorite spectrum that we've taken so far. I tried to get this as a henna tattoo, and the henna artist thought I was nuts and stopped talking to me. But this spectrum tells us about, it's lovely. You can see carbon, hydrogen, oxygen in this galaxy. There's nitrogen, which there ought not. It's weird. We're able to compare this galaxy to galaxies in the nearby universe and understand what's different. How different were things in that first couple 100 million years after the Big Bang? In these galaxy clusters and in these deep fields, we see thousands of galaxies at once. This is currently my favorite image that we've taken so far. This is a stack of a bunch of images of a galaxy cluster, Abell 2744. This is one of the very deepest images that we've taken. And I'm just going to zoom in for a bit, and I'm going to encourage you to go download it to your own computer. And then on a day when you're having a rough spell, just wander through it for a while. You can really take hours just working through the thousands of galaxies, which, our galaxy is one of out there, and get a sense of the scale and the majesty of the universe. It really is just fantastically gorgeous. Okay. We can also study galaxies in the nearby universe. Those galaxies are easier to study in great detail. So there's a black hole, a supermassive black hole in the center of that galaxy that is fueling, has an accretion disk that is eating matter. That's why it's glowing in the center. We can also study how stars die. This is a remnant of stellar death, the Cassiopeia A supernova remnant. When stars die, they give off elements. Massive stars, in their dying, synthesize the heavy elements. That's great, because we're made of them, right? You don't get carbon and oxygen and nitrogen out of the Big Bang. You need stars to make those elements. And so one of the things that the telescope is doing is seeing how those elements have built up with time. There are there are none after the Big Bang, and there's lots today. We live on a rocky planet that's made of those elements that were made in the hearts of stars. On the right panel here, this is from my own work. The donuts, these are galaxies that have been gravitationally lensed into Einstein rings that look like little donuts. I haven't had dinner yet, so there's maybe a little peckish. And the right side here is a map of where the nitrogen is. It's telling you where the elements are of nitrogen compared to hydrogen, which is telling us about where the elements are building up inside this galaxy. We can also, as we go from the very distant universe to closer to home, we can study how stars are born and how stars die in our own galaxy. This is the cosmic cliffs. It's a star-forming region in our own galaxy. It's a really spectacular image. What's going on here is stellar birth and stellar death and all at the same time. At the top, off the field, are some really massive, really hot stars, much, much hotter than the sun. They only live a couple million years and then they blow up. And they are spewing out really hot ionizing photons that are destroying the birth clouds where they were born. So this is both a stellar nursery, a site where stars are born, but it's a site where stars are then destroying their own nursery. But you can see new stars being born in these, if you just walk along these cliffs here, you can see new stars that are getting born in that compression of the gas. So it's birth, death, destruction. There seem to be processes that we are trying to understand but don't yet about how these processes seem to regulate themselves. The galaxies are forming stars at rates that it's like a regulated engine that we don't really understand. So that's one of the things we're studying is how stars are forming. We can also study how planetary systems are forming around those stars. This is data that came out on Monday. This is brand new data of a fomalhaut, which is a big star that we have masked out. It's the black dot in the middle that's missing. Just imagine it's a really expensive thumb, okay? You block out the light. It's called a chronograph. And with that technology, we can get the star to not be so bright and see the stuff around it. And so by blocking out the star and looking at it, we can see these disks, which are much like our own solar system, right? We have an asteroid belt, we have a Kuiper belt, we have these belts where there's asteroids and comets. We're seeing that, but in a really young system where it's still forming. So we're able to study how planetary systems and planets form shortly after their star forms. This is so that's a really lovely result that's new this week. And that's what we had before, right? That's data from the Spitzer Space Telescope at the same wavelength. So that's the picture that we had before and we thought we were really excited about and was great. And this is what the Webb telescope is able to do. Okay. We can also study planets orbiting other stars. We now know that planets are as common as stars. So look at the night sky, and for all those stars you see, on average, there's a planet for every star. We can study through this technique of transit spectroscopy, where we look at this, we study the star, we pick out planets that are going in front of their star from our perspective, and we compare what we get, the light that we get when the planet is in front of the star and when it's not in front of the star. And what you're getting is that starlight that went through the atmosphere of the planet and gets to you, that difference of those two little rainbows, the two spectra. And so we're able to see through the atmospheres of planets orbiting other stars and see what they're made of. And so on the right is the result to that. That's a rainbow. So we've got bluer light on the left side and redder light on the right side, and then how much of it is how tall that plot is. And the spikes there are all made from different molecules. And so this is a planet where we can confidently get carbon dioxide. Now this is not a planet that we ever want to live in. This is a 1,200 degree Saturn mass planet. All right, so most of it is not a place that you want to live, but it is how we can learn about planets that are nothing like our own. We don't have planets like that. We don't have 1,000 degree Saturns in our own solar system, that we can understand how planets are born and how they evolve, right? So we knew about the water on this planet, but getting the carbon dioxide was something that we had never done before. And then all right, we're talking about big planets. Let's go closer to home. This is actually one of our first images from Jupiter, just a very clear picture of the outer planets. In fact, we are taking data of the outer planets that we haven't had data that good since we launched a satellite to go to those planets. And so here we have data from Uranus, which is a very weird planet that we hadn't seen since we had a flyby with Voyager. So really fantastic data where we can study the rings, we can see the weather on this planet and how it's been changing, and understand what not only planets around other stars, but planets around our own star. Sorry, on the right there is just showing what it looks like with galaxies and stars in a nice field. Just very, and so folks have been very busy taking spectra of these to, again, understand what the rings are like, what the atmospheres of planets in our own system are like. So that's it. That's what the telescope was built to do, these 4 main science goals, and that's the data showing that, yes, indeed, it's able to do that. I'm going to close with just a minute or two of my own science, in part to show that, I'm not just standing up here telling you about the telescope, but I get to be a user too. These are data that we took of a lensing cluster that is where you can see the really stretched out red distorted galaxies. Those are in the background. There are some other galaxies from that program. There are 4 galaxies in our program, and you're seeing them in the near infrared at the top and in the mid infrared in the bottom. They're really gorgeous, and the stuff that we can understand, on the left we have what the stars are doing. Again, this is an Einstein ring. We're seeing it, it's a donut. We're seeing it distorted by the galaxy that's in the way. In the middle, we see what the dust is doing, so we can trace the dust in that galaxy and understand what the gas and dust is doing. And then on the right is where the ionized hydrogen is doing. So that's the hydrogen that has been heated up by stars. That's where the new stars are. And so we're studying not only galaxies as little faint fuzzies that we can barely study, but really studying them in great detail to understand how they form their stars and how they build up their heavy elements over time. So what's next after this? We anticipate a long lifetime with the Webb telescope. You should ask me how long. The answer is we don't know, but I can tell you that I can give you the longer version of that answer. We have fuel for at least 20 years of science. We've measured the performance. It almost across the board exceeds our expectations. The telescope meets all of its high-level requirements and is doing fantastic science. I will say that, it's clear to me that most of the results we've had so far show the capabilities of the telescope and that the really big discoveries are coming, that we have been steadily executing the science and folks are now working around the world, working very hard to turn those observations into papers and discoveries. And so as you, in the months and years ahead, as you see things in the news about the telescope, you're like, Jane said that the big stuff was coming. So because we're really just getting started in a lot of ways. The Nancy Grace Roman telescope is scheduled to launch in 2027. That's a telescope that in many ways is a good complement to Webb. It will study dark energy and dark matter, which are these 2 very puzzling things that most of the universe is made of that we utterly don't understand. And the technologies to build the Webb telescope, we know how to build deployable telescopes that unfold in space and that we can build them with segmented mirrors and then interferometrically phase them once they get to space to get them to work like one telescope. That's exactly the technology that you need if you use it to look at the kind of light we can see instead of the infrared light that Webb sees, to go look at, several dozen Earth-like planets around sun-like stars and figure out whether there's life on those planets. That's something that the Webb telescope cannot do. We cannot find life. We're just not gonna. It's the wrong wavelengths, we weren't built to, that's not what it's supposed to do. But you can build a telescope that has all the same pieces, right? That has that unfolds in space, that's built of segments, lots of hexagons, that is able to study 40 or 50 worlds and see whether any of them have the evidence of life. And so for me, that's also one of the big contributions of the Webb telescope, is showing us that all of those technologies for sunshields and for deployable mirrors they work. We would just need to design and build it. And that's what we have an every 10-year process to figure out what are the most important priorities for astronomy in the next decade, and this was the top recommendation. So I'm going to close here with a couple big points that I hope you take away. The Webb telescope is the most powerful telescope that was ever built. It is about 100 times more powerful than anything we've had before, and it's even better than we expected. It took about 20,000 people to build the telescope over the course of several decades, and it took 600 people to get it working in space, to commission it. And I can tell you that, everyone on the project poured their hearts and their minds, and in many cases, decades into the mission. And so it's been lovely to see all of that paying off with the fantastic science. And thank you for coming here, and thank you for joining us on that process of discovery. The discoveries have just begun, and you're part of that. We try very hard to tell the world what we're discovering when we discover it, and you're also part of it because you helped pay for it. Because at least if you pay taxes in the United States or Europe, right? So thank you as a taxpayer for helping to build this thing, and and thank you for being on this journey with us. Thank you.
A fantastic talk, and being one of the leads in what is a fantastic telescope. Speaking as a user of the telescope, it's amazing. We have some time for questions. We'll run a microphone to you. I think we have the one, unless I'm not mistaken. No, we've got two. Okay, I get to keep this one. Questions? Please put your hand up if you have a question.
Just this week, there's been a lot of news about an exoplanet. I wonder if you know anything about it because your telescope was studied with that. Was the one that studied this?
Sorry, can you say the question again?
Exoplanet.
What about it?
Just this week, there's been a lot of news about an exoplanet, and the JWST was what was studying this planet.
So we are spending about a quarter of the first year of science studying exoplanets, planets around other stars. So it is a large component of the science mission. And there's a new result out this week with participation from scientists from the University of Chicago, in fact, studying the atmosphere of one of those planets. So the big picture here, I will tell you that I have been busy on this visit and I haven't had a chance to finish reading the paper, so I'm not going to pretend that I have, okay? I got through the first third, and then it is one of a number of great papers that are coming out with analyzing this fantastic data where they're doing this technique of looking at the atmospheres of the planets and looking at the atmospheric composition. So I would say that there are more. That was one. There have been quite a few others. There are more coming. It's a quarter of our science case in the first year.
How to divvy up the science budget, time budget?
Sure, who gets time? And what do we study?
Who gets time?
Exactly, that's a great question. It's also an important question for a bunch of reasons, right? We want to be doing the best science, and we want to do it in a way that's fair and doesn't let our own biases get in the way. It used to be that telescope time, 100 years ago, was only available to a few dozen lucky people on the whole Earth. And you were either in that group or you were everybody else. And as you can imagine, that's not a great way to do things. It's pretty exclusionary. So the way we do it now is that we invite people to pitch us ideas, and in teams to pitch us ideas. And so we issue a call for proposals. And this year we got 1,600 proposals in response to that. We offered up 5,000 hours of observing time. We got 7 times that, which of course means that 6 out of every 7 teams is going to get a no, right? That's the hard part. As a proposer, that's really hard, right? Because you put in, we ask for, tell us your best ideas. So what teams do is write about a 9 or 10 page essay, a report saying this is what we want to do and why. Here's our good idea. We want to use the telescope this way. We want to use these science instruments. We want to look at these targets. And at the end of the day, we're going to learn this, this, and this, which is going to help us understand stuff. Okay? And then you send a computer file that has specifications for how you want to, what setup you want for the telescope. Okay? So we got 1,600 of those proposals, and then we get about 300 people to donate their time to us, experts from all across astronomy and planetary science, to sit and read all of those proposals. The average person gets between 70 and 100 proposals to read and rate them, to give them a grade. And then they meet together on Blue Jeans and talk about them, argue, try to understand them. What's this proposal? I didn't understand. What's it doing? And it's this peer review process. In order to minimize implicit biases, you're not allowed to say who you are. And the panel is secret too, so that they can't be lobbied. So that's done to get rid of all the biases we carry around in our heads. And so at the end of the day, we get a ranked list of what the 300 people who each agreed to read 100 proposals thought was the best science. That's a pretty laborious process. We just finished it, and we just today announced who the winners and then 6 times more the losers for the second year of science will be. But it's the fairest way that we can come up with to give out that time. In this year, we have about 250 teams won, right? And so those teams will get to do their science. We do some checks to make sure that those are actually feasible. What they proposed is actually feasible, but that's pretty much it. And so that's how we decide in a year what we do, like the big suite of what we're doing. And then every week we build a new schedule for what we're going to do next week. And that's just based on as efficiently as possible going from one target. So we pick targets that are close together on the sky and are observable to the telescope on a given day. And we spend a lot of time trying to make that schedule as efficient as possible. But in a typical day, we might observe a quasar in the morning for a couple hours, and then we go take some calibration fields, and then we go stare at an exoplanet for the rest of the day. And then in the evening, we go do something completely different, right? We go study asteroids or something. I kind of like that when I look at the daily schedule, and our schedules are online, you can go look at them, because it's this total potpourri of astronomy that is just what's observable, what's close together on the sky, and what can we jam in the schedule as densely as we can. You go to the Space Telescope Science Institute.org, but really if you Google JWST weekly schedule, you can find it, it's there. There's also a Twitter bot that just takes that schedule and tweets it out like every couple hours, right? Like right now I'm observing blah, which is just off the weekly plan.
Hello, thank you so much for your time with us today. You shared quite a bit about the successes that this telescope has had, and that's phenomenal for all of humankind. Can you share with us a little bit about some of the setbacks that you faced during your involvement in the project and what you learned from it? Sure.
So I joined this project in 2010. I moved from California to Maryland to work on it, and within about 2 months of me getting there, the mission already almost got canceled. That was an interesting way to start. And like my first meeting where I said, can I come along to senior staff to see what it's like? They were like, sure. And the project manager got fired in that meeting. So he knew it was coming. They reassigned a new project manager. So it was a really interesting time. The main challenge is that it cost $10 billion and it wasn't supposed to. It had been promised to cost less. And so for years, it was running with not enough money to actually finish building it. And so part of that, I think, we talk about how that came to be. I would say these telescopes are transformative. They're not cheap. Initially, there were some expectations that maybe we could do this much, much cheaper than had ever been done before. And that was before my time, so I don't really understand how that came to be. But in fact, it costs between $5 and $10 billion to build something like this, which is a lot of money, right? That's several tens of dollars from every taxpayer, right? And there's a lot of other national priorities. So that was the main challenge, was that, so there were technical challenges that led to that costing what it did. Some of them in retrospect we could have prevented. Some of them are just the fact that what this telescope was really hard to build. Part of that is the fact that The cold part is, is about 260 degrees different from the hot part. And keeping those two parts very separate is a very challenging thing to do. It's also really hard to do the deployments, right? Folding up that sunshield and having it deploy and not get stuck. And it got stuck in some of the tests, which isn't something we didn't hide it, but we didn't exactly talk about it. It didn't work in all the deployments. It worked on the last deployment, and then the second time it worked was in space. That was technically a really hard thing to do. There were also some engineering errors along the way. There was we do shake tests. You take the whole thing and you put it on a shaker and you shake it like it's on the rocket. You try to make sure in the testing that you're meaner to it than anything space can throw at it. So you shake it like a little bit worse than the rocket will give you. You hit it with 140 decibels of noise to simulate the noise of a launch, which can be more damaging for some things. And you put it in a vacuum chamber, most of it, and chill it down to the expected temperatures. Well, when we shook the telescope, when we shook the sunshield and then unfolded it, screws came out, like on the floor out. There are 1,000-something screws that hold that sunshield together, and there was a problem with how the nuts attached to the screws, such that they could shake themselves loose. So we lost more than a year of schedule. I think it was about a year, but it's close to a year because of screws. But it's also a little piece where every piece is important and you have to get all of it right. They didn't put enough turns on the thread, right? So that's something where something really simple can have a really profound impact. So I would say that, but we tested it, right? We knew that was the case because we tested it on the ground and it wasn't, and then we went back and fixed 1,000 tiny screws and made sure that that error wasn't anywhere else on the telescope. And when we had issues with deployments, we went back and figured out why that was happening and either redesigned it or checked to make sure there wasn't more of that. So it was technically a really hard thing to do. Once it got up, oh my God, the engineers did such a fabulous job. It was all better than we expected, right? There was only 1 or 2 nights that were scary during commissioning. Pulling out the booms was scary for the sunshield. That was a little hard. There were some indications that it was stuck. We were only worried about that for a couple hours, but there were a couple pretty scary hours. But we had data from test on the ground that showed that, yeah, that sensor can be a little weird. And also we had thermal data showing that, well, this part's getting colder. Why is it getting colder suddenly? It's because the sunshield had come out, right? And so the temperatures were changing fast. And so the thermal folks are like, oh no, look at it. It's fine, right? So it was amazing that, so that was a scary day. Pulling out the sunshield was a 16-hour shift on New Year's Eve, 2021. That was probably the scariest technical moment. And then most of the scary was on the ground, that either it would be canceled or that it wasn't working right in test.
Hello, Dr. Rigby. How are you doing? Well, I was looking at your presentation, and I was looking at the overall work of this, and I had 2 questions. Since you didn't go into the building of this telescope, I was wondering, is there a book or paper that deals with the engineering, the details and operations of the telescope? 1. Mm-hmm. And the second question is, where would I be able to find more information on the Nancy Grace Roman Telescope and the Habitable Worlds Observatory?
Okay, so the first question, is there a good book? There isn't yet. There is a book coming out that Chris Gunn, who is the official NASA photographer who took the beautiful pictures of the telescope that you can find on our Flickr page, they're coming out with a book of his photographs, and they're beautiful. I really love the ones where there's people reflected in the mirror as they're building it. It's just great. So his book is coming out. That is much more the sort of glamour shots and less the how we built it and the struggles along the way. I am not aware that there's a book yet about that. Somebody should write it. It would be good. The other question is about what can we find out about Habitable Worlds Observatory? The short answer is that there isn't, well, there's a short answer. The easiest way, I think the way to look at that is to look at, it's called LUVOIR, L-U-V-O-I-R. There's a LUVOIR final report. So NASA LUVOIR final report is a technical document, but it's actually really readable because we spent a lot of time making it readable about what would it take to build a telescope that could tell you whether we're alone in the universe. And so that's a thick final report, but it's actually a really fun read, at least you think so if you're a space geek, which we all are because we're here. So that right now I think would be the best reference. This is a new enough mission that we don't yet have all of the really accessible websites, but that's where I would go.
You mentioned the technical difficulties at the beginning and the cost overruns, which are pretty substantial. As I understand it, there was one guy and one new team that was appointed to straighten all of that out. And this may be an oversimplification, but I think he did. Is that right? Not so much. So
it's an oversimplification. We also got.
What did he do, or what did they do?
Yeah. So the main thing that happened when in 2010, 2011 is that in a nutshell, the main thing that happened is that there was an independent review committee that came in and looked at what the state of the mission was, and their main conclusion was called the ICRP. Their main conclusion was that technically we were doing great, but that there wasn't nearly enough money in the budget to actually ever finish the thing. And so in response to that, the Congress had to decide to either cancel it or fund it at the level where it would ever get done. And so Congress went back to NASA and said, tell us what it would take to actually build it. NASA came back with a new cost estimate. And once you factor in and that ended up being close to the right answer. You have to add a little bit because of COVID, because everything, because COVID added to the cost. But that's the right answer, is you have to actually be realistic about the cost, and then you have to fund it at the level that it actually costs. So that was new people, but it was also a new realism about costing.
Hi. So I've always been curious about the trajectory of sort of getting there. Mm-hmm. And I recall reading that with that mid-course correction burn, they were very concerned about overshooting the Lagrange 2. And so I was wondering if your team was involved with that. And then second question is, once you're out there, obviously you have to, I know that it goes around, sort of orbits with its back or the shield to the sun. Mm-hmm. What do you do when you want to look under? Sort of like the angles relative.
Oh, I wish I had a scale model. Okay, I need a scale model. So the first part of the question is getting to the second Lagrange point, right? Getting to that lovely little gravitational balance point in our solar system. It's actually in orbit around the second Lagrange point because we don't want to be in eclipse, right? Then we're solar powered. We don't ever want to be in eclipse, right? So we're in a nice looping orbit around that point. There's only thrusters on one side of the telescope because you don't want to fire dirty thrusters next to your beautiful mirror. So we can only fire the thrusters one way. So the main way that we change the angle that we're doing the thrusters is to turn the whole telescope around, right? So there was we very intentionally asked the Ariane rocket folks to give us about 90% of all the oomph that we needed. So that if they ran hot, if the launch gave us more energy than we wanted, we wouldn't overshoot. Because if we had overshot, we would have had to turn the whole telescope around with the sun, with the beautiful mirrors pointed toward the sun and fire the thrusters, and nobody wanted to do that. There was even discussion about, do we want that contingency plan? Because we had binders and binders of contingency plans. And the answer is that is both really unlikely and we don't even, we did have, but that was not as well fleshed out because it was seen as being very unlikely. Instead, what we did is we just asked Ariane for less than what we wanted, and they delivered perfectly to a part in 10 of the 4. It was so beautiful. And then we measured that by pointing radio telescopes, the Deep Space Network, at the telescope and seeing where it was compared to where we expected it to be. And said, oh, great, it's exactly where we told it to be. And then there are 3 little mid-course corrections. One of them, it was 12 and a half hours after launch. That was really stressful because if that didn't happen, we could lose up to, depending on how bad the launch was, we could have lost years of mission lifetime every hour. So I'm not an engineer, I'm an astronomer, and so my role in this, my only role on launch day that was not just sitting and saying, go, was that we had worked out within our project science team how important those mid-course corrections were, that we were talking years of mission lifetime. And so we had charts of this, of how, as a function of how long you wait, how much lifetime do you lose. And in the rehearsals, because we rehearsed this a couple dozen times, we would rehearse every stage of this before we did it for real. In some of the rehearsals, it did not go well, and we did not get the mid-course correction done on time. And this was one of these, that's okay, that's what rehearsals are for. You practice, and you practice, and you practice again, and then you give it to the team with anomalies, and then you give it other anomalies. You basically make the team's life miserable. But we get good at that process of working through the anomalies and understanding how to get it back on track. And so in the rehearsals, this emerged to me as the most important thing for science, is that we had to get that mid-course correction done on time. A lot had to happen that first day. We had to talk to 4 different ground stations, 3 different ground stations, and then had a 4th in reserve. And we practiced, and we practiced, and we made sure that we understood, you're gonna send me this data, and I need it in this format, and you test it, and that's not the format I need, so you're gonna do it, and we're gonna test it. All these boring preparations to make sure that it works. And then on launch day, it worked flawlessly. And that was that, okay, yes, we've acquired Malindi, our first ground station, then we've acquired Canberra, and each of those stations is measuring where the telescope is, and we're just doing the trigonometry, right, of multiple ground stations. So it's all really beautiful. Yep. It just has natural limitations, obviously, because... Oh, that was the question. How do we decide where to look? Okay, that was where can we point? But you can't point all the way down. Yeah, so there's a no-go zone, right? The telescope, if the mirror is pointed this way, the mirror can never look down to the sun, right? So if I'm the mirror, okay, see, I'm the mirror here, I can look this way. The sun is down that way. I can look anywhere around here. That's okay because my sunshield, the stage, is protecting me from the sun. You can tilt the whole sunshield by tens of degrees. And that lets you see the sky, right? And so the answer to how do I see the parts of the sky I can't see today is wait a couple months. And the Earth's orbit around the sun makes those parts accessible. So over the course of a year, we can see any point in the sky. But at any one time, we can see about 40% of the sky, right? So there's an observable part of the sky now, and then in wait, and you'll be able to see it if it's not up right now. So that complicates that scheduling process. It's not just packing in, we're packing in what's observable on a given day. But it's predictable, and it's predictable, and we compute it for every object, and then that's how we schedule it.
For us to stop. So let's thank Jane again for fabulous. And also thank you to the Brinson Foundation and the Brinson family for making this happen. We really appreciate it. And thank you to you for bringing your curiosity and enjoying the evening with us. And look out for us again next year with another Brinson lecture.
Now dismissed.